Okay, today we're very happy to have Harrison Grodin. He's been at Topos in summer of 2022 working with Dana Scott and with me last year, or 2023. Always great to have him around, and we're very excited to hear your talk.
Thank you. Well, thank you for the introduction. Today I'm going to talk about some recent work I did with my advisor Bob Harper about amortized analysis via coalgebra. So I guess the goal is going to be kind of as follows. First, I want to talk about data structures and how you can think about these coalgebraically. And then we're going to think a little bit about cost analysis using this technique called amortized analysis. That I'll review. And then I guess after that I'll maybe combine them using cost algebras. And yeah, I'm happy to have questions inline. The first, I don't know, 2/3 of the talk are going to be more or less a computer science talk. So if you feel like something could be explained better or clarified, please let me know. So, okay, I'm going to start off by giving the intro to my example for the day, which is going to be the Q data structure. So a Q data structure, do people know what a Q is? Kind of? So a Q maybe has like, yeah, first in, first out. So people call this, FIFO, first in, first out. So you put something in and then it comes out before the other things that came after it. And you usually have two operations for a Q. So you have like NQ, which maybe I'm going to say takes in an element of the data structure. I'll represent the states as D. And it maybe gives you, I'll write it in a kind of curried way. It takes in a natural number, which is the element, and then it'll give you an updated state where the number has been included. And the other method, if you want to think object-oriented about this, would be DQ, where you'll take a data structure state and then get a natural number and an element, the updated Q where that element's been removed. And I'll assume if the Q is empty, we'll give back 0. This is just a choice for simplicity today. So this is a signature in the computer science sense. Oh, yeah.
Can you say NQ again? I don't know the difference between the single arrow and the double arrow.
Oh, yeah. I'm using this for the exponential and this for the morphism in the category. It doesn't really matter.
So it says for every, I NQ a piece of data, and then for every natural number.
So D is going to be the data structure itself.
Okay.
So D is going to be like a Q, a particular Q, and you give me a natural number, and I'll give you another particular Q where that number has been incorporated.
Cool.
And then here I could give you a particular Q. It'll take a number off the front of the Q if one exists, and then it'll give you the updated Q.
Natural numbers.
Yeah, we're queuing natural numbers as our elements. So this is a good, oh yeah, question.
Why do I care about the difference between an exponential and a morphism?
I'm not going to care that much today. It's going to come up in a subtle way later, so I wanted to be precise.
Okay.
But if you think of this like a single arrow, if you're like a functional programmer, that's totally good.
Great.
Okay, so if I wanted to think about this, using category theory, I might start writing this signature using a functor. So I would maybe give a functor sigma, because it sounds like signature kind of, which is, I'll say on sets. And I'll say that sigma of D is going to be the product of the things on the right. So a product is kind of like a choice between two things. I can allow you to either NQ, if you take the first projection, and then I'll give you this function nat to D. I can also allow you the option to get a nat along with a new data structure state. So the signature represents the stuff you get out, kind of. The D on the input is kind of uniform in all the methods, so we leave it out. And then we can talk about implementations. Oh, yeah.
Cross is and, usually.
Yeah, it is and, but from the user's perspective, it's kind of like an or. If I'm a user and I get a product, I can choose to take the first projection or the second projection. There's a little bit of a duality. This will actually come out a little bit more later. But here it's behaving a little more like an and, where I have both things.
Yeah.
And here it's a little bit, I don't know, I still have both choices. I don't know. I see your point.
I mean, maybe a way of saying that is like, it's a cross in the middle because you're like loading things into a library. And you're loading two things into a library, and they both need to be available. But the caller will pick one of them.
Exactly.
And that's their business.
That's exactly right. Yep, exactly. So the caller gets to choose which element of the tuple they want.
Yeah.
Exactly. So okay, this is the signature only. But of course, just having these types doesn't really tell us what the data structure is doing. So to implement the data structure, we're going to use a coalgebra. So let me just write a quick definition. A coalgebra, or maybe a sigma coalgebra, is an implementation of the signature sigma. So really, it consists of a set D, and then sometimes I call this a transition map, if that's okay, delta, which goes from D to sigma of D. So the signature over here describe these two methods, and we say we'll take in a data structure state, and then from that state we'll offer these two methods. We'll offer you the NQ, which lets you put in a natural number, or DQ, which lets you take out a natural number. Fair so far? So let's give an example of one of these. So first I'll choose, maybe I'll say it's a tuple d delta. So one example, well, how do you want to implement a queue? Maybe it's just by a list. So I would say something like, I'll choose this kind of specification coalgebra, which I'm underlining the S to emphasize the letter choice, but I'll say it's the specification. I'll have S and sigma be the set and the transition map. So I'll choose that maybe S is a list of natural numbers, which I'll just abbreviate as list. And then I can say the transition map is defined by implementing both methods. Question?
I guess you want to say that the DQ should be n times d plus 1, right?
Yeah, I'm just going to give back some default value like 0 for the natural number. I would do that if I was being a little more precise, or if I wanted a different behavior. I'm simplifying a little so I don't have to worry as much. But yeah, definitely that's a valid thing to do. So the way I'm going to implement sigma, well, let's write the type of sigma first. It's going to have type list to sigma of list. And I'm going to use this technique that computer scientists call co-pattern matching. If you know pattern matching, it's the opposite.
List of naturals?
Yeah, list of natural numbers. I can write it here, but I'm going to write list enough that I don't want to do that too many times. So I'm going to use co-pattern matching. And the way you do that is you kind of just explain how you would use sigma and what should happen in each instance. So if I had sigma applied to a list L, and I wanted to take the first projection, which I'll kind of name here NQ. I'll abbreviate ENQ. And I wanted to NQ. Now I guess I'm implementing this function, so I'll say what happens when you get an element n. And I'm supposed to give back another element of D, or another element of the set that we chose for the states. And here we chose that it's a list, so we have to give a new list. So I will pick that this list is just going to be L. I'll write plus plus for append, and then I'll write a little singleton list n that goes at the end. Is this a fair thing to do? And then if I wanted to implement DQ, I'll mix pattern matching and co-pattern matching. So I'll say that sigma on the empty list, DQing, is going to be 0 as my default value, and then I'll keep the empty list. And sigma on a non-empty list, which I'm going to write n : L. If you're a functional programmer, maybe you recognize this as cons. If I DQ this, then I'll get back the element at the front of the list, which was n, and I'll give back the remaining list as L. So just as a little refresher, by the way, lists are inductively generated by nil, which is a list. And if I write this using infix notation, it's double colon, which we pronounce, this is nil. Double colon, we pronounce cons. And this is like nat cross list to list. So there's kind of an asymmetry here, where even though it's annoying that cons is a symmetric symbol, but the first part is an element of the list, and the second part is going to be another list. So accessing stuff at the front of the list is easy, and putting stuff at the end of the list is hard. So I'm going to start indicating some cost things in red. I'm going to just flag this fact. Appending to the end, putting a number at the end of a list is expensive, because the longer L is, the longer it's going to take for me to get all the way to the end of the list. So even though this is a correct implementation, it's not the most efficient.
My glasses must be a little cloudy. Where is the coalgebra?
So the coalgebra is sigma. Sigma is the coalgebra list to sigma of list. So a coalgebra we said was a set, here I called it S,
Okay.
and then it's this transition map. I defined it by components, so it's maybe a different notation than we might always be used to, but it's defining a function, or it's defining a morphism list to sigma of list by component. So it's saying sigma of a list, and then it's giving the NQ component and the DQ component.
Why is this co-pattern matching? I thought co-pattern matching was like where you have like the co-inductive destructors.
That's true. Just think, instead of it being a co-inductive destructor, think of it just being destructors for a tuple, where the first component is called NQ and the second is called DQ.
Oh, so it's like a trivial case of co-induction.
Exactly. It's like a co-induction, but where you don't co-recur.
I'm seeing so much like come together.
Yeah.
Yeah, because product is like co-product then.
Yeah.
Sorry.
That's true. Cool. All right, is this a fair implementation that we're kind of happy with? And do we kind of agree also that this is inefficient? So the next goal is going to be to find a more efficient representation, a more efficient coalgebra. So we can implement Qs in a way that would hopefully behave faster. Let's talk about what we could do. Well, I'll tell you about the implementation a little bit, and let's see if we can derive some intuition for it. So our other running example is going to be called a batched queue, which is like the interesting data structure for queues, maybe, for functional queues. So for this, I'm going to choose something that you might be surprised by. I'll choose D to be list cross list, or maybe sometimes I'll abbreviate that as list squared. And the intuition is going to be dump all of your NQ'd elements in the first list and receive all of your elements that are being DQ'd from the second list, which sounds like it's too good to be true, right? So I'm hopefully going to implement delta, which goes from D to sigma of D, and delta of list inbox and list outbox dot NQ n is going to be really easy. It's amazingly easy. I'm just going to put n on the front of the inbox and leave the outbox alone. What? So okay, how do you get stuff out of this thing? Well, as long as the outbox is non-empty, so if it was n on the front of an outbox, and you're asked to DQ, it's extremely easy. You give back the front of the outbox and leave the inbox alone, and the outbox now lost this front element. What's the problem? I feel like I'm doing a magic trick almost. How did this turn so easy? Or what's wrong?
What about the case where L in is DQ'd?
So you're not allowed, or I don't know, I'm implementing it such that you're not allowed to DQ from L in. I get to choose that you go from the output. But what if the outbox was empty? I was supposed to give both cases, and I gave the easy case first, which was that the outbox is non-empty. But what if the outbox was empty, and I was asked to DQ from that? This is the trouble case, right? Because I suddenly I have a full inbox of stuff that I've wanted to NQ. So when I DQ, I'm hoping that it'll come from that, and there's nothing left in the outbox, so I have to do something expensive. I have to do a complicated idea, which is break into two cases. So I'm going to break into cases on, I'm going to look at reverse of the inbox list. Okay, if the reversed inbox list is empty, then I'm kind of out of luck. So I'll say you have an empty queue. The outbox was empty, the inbox was empty, everything's bad. So you get 0, just like we did over here. And the updated state is just 2 empty lists. But there could be a luckier case where reverse of the inbox list is now some number on the front of a new outbox list. So if I flipped the inbox around, then I could give back the element that was at the end of the inbox. It was at the beginning of the reversed inbox. So it's the correct number to be giving back. And I can make the new inbox be empty, and the new outbox be this reversed inbox minus the first element. So I think this also works, and it has this nice property that the first two cases, the NQ and the easy DQ, are free, right? As long as my cost model only, I'm going to care about appends and reverses, but so appending a singleton is expensive, and reversing a list is expensive, but I'm allowed to just put something on the front for free. So suddenly, okay, this reversal step is expensive, but in a lot of cases, like in the common case where the inbox and the outbox are non-empty, it seems all right. So for example, if we started out with an inbox that had three, let me number it differently. If I had my outbox have 1, 2, and my inbox had 3, 4, 5, where this is kind of the front, like the top that I can easily take from, then if I were to do a couple DQs, so if I did a DQ and a DQ, I would end up with 5, 4, 3 still in the inbox, and those operations to take 1 and 2 out would have been free. It's only after I do another DQ that the inbox gets emptied out and the outbox will have 4 or 5, since we'll have DQ'd the 3. But most of the operations, in some hand-wavy sense thus far, seem to be pretty cheap. They seem to be free. It seems like I rarely encounter this bad thing, whereas before, I was encountering this bad NQ case every time I did NQ. So I've turned an always bad thing into an occasional bad thing, which seems like a broadly good idea. Are we on board with this idea? So let's first confirm to ourselves that these two things actually match up. How am I convinced? Let me even say something else before I do that. Do you kind of believe that the specification is a good specification for queues? It's inefficient, I must admit, but it kind of models what I would hope a queue to do in an easy to read way. This thing, I don't know, I maybe convinced you that it's a correctly implemented program, but it has some more complexity to it for sure. So I would hope that I could convince myself that this implementation is kind of a faithful representation of this, even though it has additional complexity.
So your implementations are coalgebras and your specifications are also coalgebras.
Yeah, so they're really two separate, they're just two implementations. And I have a simple one that is not so efficient, and a complicated one that I hope is a little more efficient.
What is a specification but just a very simple and inefficient implementation?
Exactly that.
Yeah.
A specification is just a simple and probably inefficient implementation. Yeah. So I would hope that I could connect them up. So let me try to do that. The way we do it is using a morphism of coalgebras. So a morphism of sigma coalgebras consists of, well, a function f. Let me say that it's going from d delta to s sigma will consist of a function f from d to s, as well as a constraint that if I considered using delta, so if I consider using the efficient representation, in parallel kind of to considering the specification, it doesn't matter if I converted to the specification before or after. So the idea is I could have said, use my efficient thing to do a DQ, and then I could convert to the single list approach. Or I could have said, just convert to the single list approach, it's too complicated, and then DQ in that obvious way. And it won't be discernible which one was which.
I feel like I finally understood something, because when you started over there, I was like, so Harrison, I could have like the trivial coalgebra, and the coalgebra.
That's true. Yeah.
You haven't told me anything.
That's true.
Now
I'm telling you.
A Q is a coalgebra and a morphism into the specification.
Exactly. Yep. So yeah, exactly. This is kind of the description of a queue is not just the types. It's also the operations implemented in this way. So if I wanted to convince myself I have a correct Q, exactly, I do something maybe more complicated, but I have to give you a morphism into that coalgebra. So does anyone have oh yeah, question?
Can you return quickly to something about specification being simple and probably inefficient?
To the list one? Yeah.
Are you endorsing that across in this context or across?
In this context. For a stack, a list is a very efficient representation.
Well, no,
Oh.
I guess to me, this is perhaps a bit low-tended, but a specification is a higher-level declarative description of the observable behavior or something, which may be in a completely different language from the implementation.
That's true. Yeah, this is a good point. I would say, so the way I usually think about a specification is a simple, like, toy implementation, because I feel that it should precisely describe the behaviors that I would expect so that I can give a morphism and show when I implemented it correct, like when I have a correct other implementation, but I don't know.
What about if you're specifying something as a type, you have reach-dependent type theory?
Yeah, so
does that meet the model?
It does. You would just look for all of the, you would look for sigma over all coalgebras equipped with a morphism into this one, which is maybe cheating. Of what? I don't know about this. Oh, can you say more?
Rectifier is what's used for converting AC to DC.
Mm.
And so basically, this reminds me of the way that a rectifier works in a circuit board.
Can we talk about that afterwards? Because I'm very interested. I don't know anything about electrical engineering. Question, David, maybe?
If D had been empty, this also would have worked. Like, don't you want some map from S? Why did you do a map into S instead of out?
So if D were empty, you can have it be empty if I only ask you to implement NQ. But given that I asked you to implement DQ, which has to generate a natural number,
There's no map from D to sigma D. D is the empty set. Then
why am I saying this? That's a good point.
Just mapping into S, you don't know that you've really gotten all of it.
That's true. Let me think about that. That's a nice point. Oh yeah, I was thinking if you can pick terminal, like you can pick singleton very easily, but you'll run into trouble with picking that number. But if it's empty, let me think about that. That's a good point.
Yeah.
Okay, so I want to give a morphism of coalgebras here. Can anyone, does anyone have an idea for what this morphism would be? It's really just a function from D to S that kind of faithfully represents the transformation.
Li LO goes to Li concat reverse of LO.
Other way around, but yeah. So you take the output list on the front, because over here we had our data to DQ at the front. So it'll be LO, appended, prepended before reversed Li. Is this fair? So we could check some cases of this. Maybe the NQ case is okay to check, because for this to commute, both operations kind of have to match up according to F. So we could check that if you did, do I want to do this? I guess let's do it. We could check that if you follow the top and then go down, well, let's first write what that means. Going along the top is going to be taking delta of Li, Lo. For the NQ case, we'll do an NQ of N, and afterwards we'll use F. So if, and the alternative would be, we could have used F first. So we take F of Li, Lo, and then done sigmas NQ of N. On the left side, well, the complicated NQ, or the clever NQ, it wasn't that complicated for the NQ case. I guess it just prepended. So we would have that this is equal to F of N cons Li, and then Lo over here. And F, as we defined it here, just says do Lo appended with reversed N cons Li. Versus on the other side, if we did, if we first compute F to be sigma of Lo append reverse Li, and then we NQ N, well, we can use the NQ from over there that appends a singleton to get that we have a Lo appended with reversed Li appended with the singleton N. And these look okay. They both start off, they look equivalent because they both start off with LO. And if you reversed n cons Li, that's the same thing as reversing Li and putting n on the end. Not for efficiency purposes, but as far as just checking correctness, I think this works. Are we kind of on board? And the DQ check is, you have to break into cases a little more. So I'll leave that as an exercise. But that's a confirmation that we did the right thing. Oh yeah, please. So okay, now my question for you, switching kind of to point 2, is how efficient is this? So how efficient is this new representation? So I'm going to start writing in red for cost information. How efficient do you think this batched queue is? Well, you could kind of you could think about the cost that you incur over time, perhaps. Well, okay, what's the worst case and the best case before we even get to that? So okay, for NQ, it always costs 0. I'm going to write a $sign to mean to indicate some abstract notion of cost. But NQ never does any cost. It just conses and is done. DQ is, well, sometimes it's 0. That's great. But sometimes it's, how expensive? Linear. Well, yeah, linear in the length of Li. So I'll say it just costs length of Li. But that's not so insightful. I feel like there's something else going on here. Because how often does this really happen? Like if I filled up the inbox a lot and then tried to DQ, I'd move the whole inbox over at once, and then I wouldn't do it again for ages, right? Because I'd have such a big outbox to work through. So if I drew a little, if I drew a graph of cost incurred and NQs done over time, well, the real cost would be the NQs are free, and then maybe before I do my next NQ, I do a DQ, and then I do a lot of NQs again, and I do a DQ, and it's very expensive, and then maybe you can alternate between NQs and DQs for a little bit. But somehow, there's a line that goes through here where every time I do an NQ, it's only going to contribute to one future cost. So if I'm reversing a list, I reverse a longer and longer list depending on how many things I NQ'd, and it's in some abstract sense should pretend like NQ costs 1 and nothing else costs anything. So I would hope this is a true theorem. So okay, theorem is if you do k NQs, then total cost is maybe less than or equal to k. So you could try to prove this by induction. So you would say, I'll think about a sequence of operations, and if in the empty sequence case, then it holds trivially. In the NQ case, it works. But in the DQ case, you'll actually run into trouble just proving this fact by induction on its own. Because when you're DQing, you're suddenly going to incur a lot of costs that you don't really know what to do with, even though you already did NQs that were supposed to pay in the future in some sense for this DQ. So you can prove this theorem, but the proof is not by induction directly. So by induction is not going to work. Don't try to do this directly. So what do you do instead? Well, there's this cool idea called amortized analysis, which is inspired by economics and by physics, actually, where you give a potential function. So you can alternatively say, I'll give a potential function. And the potential function is a function from, let's say, d to the integers, which tells you kind of how much cost you should be ready to incur. How much cost you have stored up as potential energy, if you want to think about it that way. So the potential is going to be the difference between the solid line and the dotted line. So this function is called phi usually, capital Phi. So here phi, at the beginning, phi would maybe be 0. Once you hit this point, right before that big jump, phi would be maybe 2 or 3, however tall this line is. And then it would jump back to 0. It would grow and grow and grow. So this is again going to be, this difference is going to be phi. And then it would grow for a while and then go back to 0. And then here it might alternate between 1 and 0 a bunch. So the potential is indicating how much cost you should be ready for a big operation to produce. Right? So the NQs were making the input list longer, which is making it worse and worse when we eventually do a DQ. And then what you do to prove the theorem is as follows. You would show that if I had the cost of an NQ plus the change in potential, sometimes people write this as the delta phi, this should be equal to 1. So if I did an NQ and consider the difference in the potential, that should cost 1. Versus if I had the cost of a DQ plus the change in potential, that should be 0. Because what was really contributing to the cost was making the input list longer. So what I mean by delta phi, by the way, is the potential of the new state minus the potential of the state that I'm in right now. So, okay, another, I guess, question time. Does anyone have a proposal for what phi could be? So we'll define like phi of Li, Lo is something.
The length of the input list?
Great, that's perfect. So it's length of the input list, because that's what's causing us trouble, right? And we can check these conditions too. Maybe I won't write it so much, but I can point over, I can, proof by pointing, I can look at the cost of an NQ was always 0, and the change in potential was always 1, because the input list got 1 longer. So that trivially works. The cost of a DQ was either 0, in which case the change in potential was 0, because the inbox list didn't change, or it was length of Li, in which case the inbox list got moved to the outbox list, so the potential went down by length of Li. Right? We started with a non-trivial inbox list, and by the end, this was empty. So I could write this out symbolically, but maybe the pointing is enough. This works out. And why does this prove the theorem? Well, if I wanted to consider the total cost, so I wanted to show the total cost is bounded by k. Well, k is the sum of the all of the amortized costs so sum over I amortized cost sub I, because I counted 1 for each NQ and 0 for each DQ. So if I wanted to count how many NQs, I can just sum up all of the amortized costs, which is either a 1 or a 0. And I know by this reasoning that this is really the sum over I of the real cost plus the change in potential. And since I'm changing the potential, I'm doing kind of a telescoping sum here, where I'm adding something and then subtracting it off in the next layer. The only thing that's left at the end is the sum of the costs plus the potential, I'll say phi n, the potential after n steps, minus the potential in state 0. I'm going to assume that the potential in state 0 is 0 if I started with the empty queue, which is 2 empty lists. So now I have that k is the sum of all the costs plus something. So that's greater than or equal to the sum of all the costs. It's a little bit of tricky arithmetic. But if you use this telescoping sum and the fact that your change in potential is bounded in this, relative to the cost and the amortized pretend cost, then you can figure out how to prove this theorem. So there's another way to think about this, which I started to do. This is stuff that's been around for 40 or so years. But another way you can picture this is, well, if I started with, well, okay, let me draw a picture. If I started with a state of the data structure, and I'm going to show a little evolution of the data structure over here, where I may be NQ1, NQ2 again, NQ2 as a second thing. I can DQ and then DQ, where I'm going to say, I'm not going to include the element that got DQ'd, I'll just silently delete that. I could imagine tracing along, starting from a pair of empty lists over to 1 in the inbox, over to 2, 1 in the inbox, kind of in backwards order. Oh no. Over to empty inbox because we dequeued. And then the outbox has 2. All the way back to 2 empty outboxes. And I can write, I'll keep with my cost being in red, I can write the cost of each one of these operations as, well, this is 0, this is 0. This was 2. And then this was 0 at the end. But I can also keep track of these kind of pseudo costs, these amortized costs that I'm pretending match up with reality, where I could say, well, I started off by doing 1 cost for this NQ in my pretend world. And then I did another 1 cost. So maybe I'll put some little mappings. That's not what I wanted to do. I can have a couple mappings. I want to make this more parallel with the above picture. So the first mapping maybe did 1 by my fake calculation, my amortized calculation. And then the second NQ cost 1. And then these 2 didn't cost anything. So if I kind of imagined joining up the real track with the fake track, and I imagine how this mapping is commuting, I would notice if I go along the real route, I end up costing 2. And if I go along the fake route, I also end up costing 2. So this telescoping sum, which I don't know, I find a little bit tricky to get right, is kind of just composing a bunch of commutative squares, maybe? So we can start to see it a little better. Yeah?
It's not always going to be commutative, though, because you might have some extra amortized costs.
Great. So you might notice, yeah, I drew a giant commutative rectangle, and it did commute. But if I tried to compose this out of smaller commutative squares, you'd kind of expect that, well, this doesn't commute anymore if I just add the arrow naively. So really, the arrow coming down has to have 1 cost associated with it to match this. And let me just do some arithmetic games for a minute and just see what happens. Maybe, OK, that adds a constraint to be 1. Now this one has to be 2. And then what happens? Then wait. It's 2 and 2. So now this can be 0 and everything's good. So somehow, OK, something crazy is happening. What numbers, what did I add here vertically? Which is the potential. So it's crazy. If you just add the potential as these vertical things, you notice, wait. It makes everything commute, and that's how you're building this. So the telescoping sum argument is what happens when you just are composing these commutative squares. So I looked at this and I said, wow, that's quite a cool thing, yeah. Maybe this is a cleaner way of thinking about amortized analysis. Maybe I can save fewer words and consolidate some stuff. So I kind of left some space here. But what I might try to do is just include the specification on the bottom. So I might say on the bottom, I'll keep empty list here, 1 here, 1, 2 here, not 2, 1. And then over here, I'll have 2 and back to empty. And the idea is my specification is going to be not only a specification for the correctness, but also for the cost. So the specification is going to not have its real cost, but some fake cost where the correctness matches the real correctness. And the fake cost that I put in the specification can hopefully explain what's really going on with the batch queue, this efficient implementation. Is this cool so far? Extremely, wow. OK, so great. I think that's where I want to be right now. Great. So how do we make this happen? So far, the dollar signs are just fake, right? The dollar signs, this is not part of anything that I did formally in the category theory. I just wrote down some dollar signs because I was trying to do cost analysis. But the project that my collaborators and I are doing is trying to create a framework in which you can formally prove statements about cost, just like we could prove statements about correctness. So this is where we get to part 3. Maybe I'll start putting it down here. So 3 is when we have cost algebras. So a cost algebra is going to be a new type of thing that we're going to replace our base category with. Instead of working with set theory, we're going to work with cost algebras. So a cost algebra is, do people know about the writer monad? If you know about the writer monad, it's an algebra for the writer monad. So I can just say that. But I can write it more explicitly. A cost algebra is a couple things. It's a set x along with a map, maybe I'll call it $, which goes from cost cross x to x, such that some conditions hold. For example, $0 on top of x should be the same as x. You know, $sign really increments the cost stored in the set x by some amount, and incrementing the cost by 0 should have no impact. And incrementing by c1 followed by incrementing by c2 should be the same thing as incrementing by c1 plus c2. So here I'm writing Blackboard C to mean some arbitrary monoid. You can think of it like the natural numbers. So that's what a cost algebra is. And a particularly important one is going to be the free algebra, which if you're used to thinking about the writer monad might be the more familiar one because it's implemented using a monadic primitive. So the free algebra, f of x, is defined as, so it's really like x and $sign here. F of x is going to be cost cross x, which is the writer monad. And then we're going to have as the function that incorporates cost, well, it has to be a map cost cross x into, well, we want to go to cost cross x eventually. So we can notice that this is isomorphic to cost cross x. And then we can say, well, just add the costs, right? If this is meant to be the counter of your current cost, you can just incorporate the cost by doing the addition onto the cost you already have. So there are other algebras too, but this is kind of a good one to think about. It's the algebra where you just keep adding to your cost counter. So now I'm going to do something a little bit dangerous, and I'm going to start mutating my board. So I'm going to use blue, and I'm going to start changing stuff we already did. So instead of being based on sets, it's based on cost algebras. Oh, and I'll write this category. This can be called, like, I don't know, C-alg or something, if that's fair. So OK, over here, I told you that sigma was a signature from set to set. No longer. Now it's going to be from C-alg to C-alg. And I have to be a little bit careful. Down here, before we had a polynomial functor, and it was all nice. But now I have to be careful with these arrows and these products and things. So I'm really going to say this is now nat powered with d. So power is kind of like it's kind of like a function, but the input is a set, not a cost algebra, because I'm assuming d is a cost algebra, but nat or whatever element type I'm working with shouldn't absorb cost. And I'll also take the product of that with nat co-powered with. So this is power, and this is co-powered with d. So here I kind of separated the meaning of times into something that's a little bit more eager of having both things at the same time, and something that's a little more lazy in letting me choose between these two things. And if you like, if your cost model is commutative, and then you get a tensor product, so you can really think, and an internal hom. So you could think of this as f of nat internal hom d, and this is f of nat tensor d, if you have that structure. So also, if you're used to thinking of linear type theory, you should start to be happy. So OK, what do we change now? A sigma coalgebra is no longer a set, it's a cost algebra. Maybe I should start like deleting the old things. And then the transition map still works like this. It's just now this is a morphism in the category of cost algebras rather than in the category set. The specification now has to be a particular, it has to be a cost algebra equipped with some structure. So instead of using list of nat, I'll use my favorite thing, f of list of nat. And then writing a map out of an f, yeah.
I'm like, I don't know, this is a little fast for me or something.
Oh, sorry. I'm just adding f's everywhere. Like the punchline is I'm just going to put,
Following that bit?
not really. Like I'm kind of, f is like the most boring way I can switch from set to cost algebras. So I'm just dumping like f everywhere. So everywhere, even if you think about over here, I just put f. Instead of nat, I have f of nat. OK, I used to have a set that I liked. Now I want a cost algebra I like. OK, f. So I'm just going to write f everywhere.
Maybe my question is,
Oh, yeah.
an example later where that I'll understand what the f is doing?
Yeah, I could even say it right now. The only thing the f is doing is making it so that, well, the subcategory, the full subcategory of cost algebras, which is only the Fs, only the free algebras, is the Kleisli category. So if you're used to functional programming with the writer monad, then as long as I put F like everywhere on the board, we're just going to be using the writer monad. So that's going to allow my programs to include the $sign. That's the only thing that's going to happen.
Yeah.
So I'm trying to make it so my programs include $signs,
Yeah.
because
You don't
$sign.
use dollar throughout.
Yeah, $signs over here are like an actual thing that every object has. The whole point of a cost algebra is it's a set, but with a $sign option. So if I over here tried to write a function, it's now like, okay, fine, it's f of list to sigma of f of list. But mapping out of an f is, f is a left adjoint, so you kind of just say what you do on the generators anyway. So I still will write the same exact code on the left, like the co-pattern matching. But on the right, I can now put $signs. That's the only thing that changed.
Yeah.
So specifically what I'll do is on the NQ, I'm going to decide, this is an interesting thing, $1 goes there. So my remark still stands, this would be expensive, but working in cost algebras, I can pick whatever cost model I want. And here my chosen cost model is that I hope my amortized specification tells me that I'm going to incur 1 cost per NQ, in the limit, and no cost for DQs. So the only thing that switching is doing is it's forcing me to be a little bit more careful with my connectives. So I have to be careful a little bit with times versus tensor, which I now have a distinction between. And other than that, I just put f like everywhere. That's kind of the methodology. So same thing here. I had list cross list. OK, I have f of list cross list. I just keep doing that. And over here, now I'm going to put like $sign length of li outside this whole thing, because I was reversing li, and my cost model says that that's expensive. So the only thing I'm doing with my blue marker is putting f's and putting $signs. So I'm making cost like a first-class notion in my programs. Yeah.
So in this specification model, the cost right now is like this theoretical. It's not the
Yes,
actual cost.
that's right. So that you should never really run the specification, you'll have a bad time. Instead, you should treat the specification as like an interface that's telling you a queue will behave like this, like Sophie said, and my queue in particular will have cost 1 for NQ and 0 for DQ amortized.
Oh, wow. So is it, do you change the costs there if you're doing a different?
You do. So this is a tricky thing. Part of the research that I'm doing is also connected, it's about connecting cost verification with general verification or maybe correctness verification that ignores cost. So there is a story here too, where you might say, I want a signature without cost at all, and then you want certain sub-signatures that include various cost information. But I'm not going to do that today. For now, just this is the signature, not for queues in general anymore, for queues with this cost. Like I'm including this particular cost. So OK, I did all these things. I have to kind of do a sweep. So what's the morphism of sigma coalgebras? I didn't really say it's a function on sets. I just said, I guess I said that before, but now it's a morphism between coalgebras. So really here, I guess I'll write what the type was before. F used to go from list cross list over to list. And what does it do now? It goes from f of list cross list to f of list. So the thing to remember, I guess I should write this maybe. If you ever see a map f of x to f of y, this is the same as a map x to cost cross y by using the adjunction. So I'm just going to write the same kind of code that I was writing before, but I'll be a functional programmer, and I'll be a Haskell programmer or something, and I'll use the monad. So I'll specifically get to output some cost, and my syntax for I'm outputting some cost is $signs. So over here, I now have to write f. What is f going to be? So OK, question. Does this commute already? Like I gave a homomorphism between these sigma coalgebras. Does this work? Like, no. Why not?
Because this is going to give me the dollars that are going down.
Yeah, exactly.
You don't put anything there, it's like $0 down, but those don't commute.
Exactly. So the tricky thing is, if you just say, well, I just convert freely between these representations, you could have that the top representation, well, imagine the middle costs were all 0. The top could have said, oh, it costs 0 to do these NQs. You switch to the bottom freely, let's pretend, and then you keep DQing, and you never incurred any cost. You made it the whole way through without any cost, which is kind of not what you want. You want, at any point, if you switch from the top to the bottom, that any cost you were supposed to have incurred eventually, like these 2 costs for NQs, you incur right now, so that the cost models line up. So the way to do that is this awesome fact where you now say, I'm going to put some dollar signs on f itself, which is dollar sign length of Li on this thing. So I think now it commutes because in addition to checking the correctness, I have to check the cost commuting. So we can, I'll do another example kind of like this. For the NQ, on the NQ side, we charged 1 over here. And then we took the potential afterwards. So, OK, I'm going to push over to this space if that's OK. I'm going to just do that. So the potential, if I follow the top and the down arrows, then I will first incur, oh, sorry, I'll do the other direction next. First, delta will incur 0 cost. And then I will use my f to incur length of Li cost. And that's supposed to be the same as first using f and getting length of Li. Oh, sorry. It's going to be length of Li plus 1 over here. I should be careful about that, because when I used delta, I made Li longer, right? I increased the length by 1. Sorry, pointing at the wrong spot. I increased the length of Li by 1. So on the right side, now I said you should you should go down with f first, and that's going to charge you length of Li. And when you go across with sigma, well, sigma said you're supposed to cost 1 amortized. So we get this equation that 0 plus Li plus 1 should be the same thing as Li plus 1, which is true. And you can also, OK, let's do the dq sanity check. We might observe that dq along the top using the real implementation, in the first case costs 0. So we have to kind of, this was NQ, and we have 2 cases for dq. We either cost 0, which is awesome, and then we charge length of Li because Li was unchanged. Or, sorry, the other route we could take is we charge Li based on the potential function. And then apparently dq's cost nothing in either case. So this kind of tracks. And then the really interesting case is this last one, where the dq using delta costs length of Li. But then when we use f after the dq, Li is empty. And then the other side stays the same. So somehow we either spent real cost or we spent potential. So we spent kind of kinetic energy or potential energy, or we spent like upfront cost or future cost, depending on if you're a mathematician or an economist or a physicist. So they're all kind of the same thing. And this is the neat observation. And in fact, this condition that I've been writing was kind of saying, well, it's if you want to be really, if you want to look at it directly, it's saying that the cost plus the potential prime is equal to the potential plus the amortized cost, which is exactly the condition that people have been saying for since the 80s. But whereas they've been like subtracting phi from both sides, so you have delta phi, we have a more like morphism, like structure preserving morphism perspective, where you just have addition. So this is maybe where I can start to conclude. Some cool things that fall out of this are you can amortize other stuff. So here we required like subtraction and commutativity when we were doing this argument, but composing commutative squares like we did over here, and using this kind of form of the equation doesn't require any of those things. You just need a monoid. So you, for example, in one of my favorite examples, you can let the cost model be strings, and then you find by this kind of argument that amortized string printing is buffering, because you flush the buffer once in a while and then you print in batches. So That's kind of cool. You can amortize other effects too. So here I worked with cost algebras where cost printing was the only effect. But if I worked with algebras where I also had structure for randomness, for example, then I can amortize randomness. And then I'll find that flipping coins now versus flipping coins later are the same thing, which is cool. Some other things happen. If you want to give upper bounds, which is a common thing in amortized analysis, sometimes you don't want to say that I know the exact cost being 1, because there can be cases where you get lucky and the amortized cost is an upper bound. It's more than the actual cost. And then you can work with colax coalgebra morphisms, which just means you have a 2-cell here. It's kind of like a cost inequality rather than a cost equality. You can do, if you want to have, you can do the same story with algebras if you want to have methods combining stuff rather than splitting off, or even with coalgebras for a profunctor if you want both covariant and contravariant things. The story, like, luckily the story is just super general and seems to work all the time. Oh, another cool thing also is that you get composition out of this, where typically in the traditional presentation that I was giving you, phi is this meta idea. It's like this function you use in your analysis, but it's some mathematical function into the integers or something that's not part of your program. It's just an analysis tool. Now, f is a real piece of code. And moreover, instead of taking a data structure state to something kind of inert like a number, you're taking one data structure state to another data structure state. So you're both talking about verifying the correctness and the cost. And if you furthermore said that the batched queue was implemented in terms of some other amortized data structures, you can compose potential functions, which composes the cost and the correctness. It composes the mathematical potential functions and the behavioral correctness. So the kind of, the TLDR is really said there in the beginning. Amortized analysis is just coalgebra, it seems. So if you're ever interested in doing amortized analysis, just work with coalgebra or really just work in the category of cost algebras. And anytime you have a data structure, every time you have a structure preserving homomorphism, the fact that it's preserving the cost is exactly checking this kind of amortized condition on long-term cost. I think that's about all I have to say. I have a few more minutes if we have some final questions, but otherwise, thanks for listening. Questions?
We referred to the joint paper with Bob Harper. Does it include this kind of?
It does, yeah. This example, so I have a paper at MFPS this past summer that is with my advisor, Bob Harper, and all of this is written out there with some other examples too. So if you're interested in this and want to see the full write-up beyond this one example, there are other examples and some generalizations like I discussed. It's all written up. It's that. It's amortized analysis via coalgebra by me. Question, thought?
Yes, I was wondering, is there a good example where you don't use, like, of a real cost algebra around f?
Yeah, that's a great question. I wondered this also. There are, but it's a little tricky. So another perspective that you can take that's taken by Paul Blaine-Levy in his work called Call by Push Value is that when you're working with these algebras, you can think of those like lazy types. Like the algebras are lazy. So the product over there was kind of a lazy product. And oftentimes, so for classic amortized analysis, it looks like you always want f. Like you just should put f everywhere and work in the Kleisli category. But if you wanted to lazily avoid doing some computation, you could pick, for example, that your carrier is a lazy product of two f's, for example. So there's one example in the paper like this, where you have something kind of like an f of list cross f of 1. F of 1 is just cost. There's no other data stored. And this lets you say, over time, like every time I implement an operation, I can see if I needed to use the list that I had, or if I can hedge my bets and lazily not incur this cost until I absolutely have to. So another title for this talk/paper could have been amortized analysis is lazy cost or something. So you can use other lazy data structures to avoid cost, and it's the same kind of idea. But F is really the common case. If you find a data structure or something where you get a serious like asymptotic improvement by doing a non-F type, I'd be really excited to know. It seems like right now it's like lets you save on constants, but not much else.
All right.
All right.
Harrison once again.
Thanks, everyone.